Hello, how you doing? Have you seen or heard that neural network activation functions are always nonlinear, and you're not quite sure you know exactly why this is? Well, if so, then watch along with me for the next few minutes, and I will quickly get you up to speed. Okay, let's get started. So first, what do neural network activation functions actually do? Well, in simple terms, activation functions help neural networks make sense of complex data by adding flexibility to the model. I have a video called Components of a Neural Network where I describe conceptually how activation functions work within a neural network. Check this video out if you want to go deeper. But in summary, a neuron in an artificial neural network computes the weighted sum of all its inputs, adds a bias term, and applies an activation function. The bias helps the model shift the activation function to fit the data better. The activation function determines whether a neuron activates, passing its signal to the next layer in the artificial neural network. So in real-world neural networks, are linear activation functions ever used? Well, the answer is no, not really. You see, linear activation functions produce outputs that are directly proportional to the input, which limits the network's ability to learn complex patterns. Stacking multiple layers with linear activations collapses into a single linear transformation, so a deep network behaves just like a single layer model. Linear activation functions just can't model nonlinear relationships. And it turns out the real world is complex and nonlinear. In summary, linear activations can only separate data with straight line boundaries. Take a look at this example data set in 2 dimensions. The purple points represent a nonlinear real-world relationship between input X feature and an output Y. The white line shows how a linear activation function can only fit a straight line. This linear function fails to capture the complexity of the data. On the other hand, nonlinear functions give neural networks the power to understand and process complex data. Look at this same example data set with a nonlinear activation function. Here you can clearly see the difference. The neural network with a nonlinear ReLU activation function, in this case, captures the underlying sinusoidal curve much better than just a straight line. Unlike a linear activation, these nonlinear activations give the network the flexibility to approximate complex real-world relationships. So what are some commonly used nonlinear activation functions? Well, although this list is not exhaustive, sigmoid, tanh, ReLU, and softmax are quite common. Each of these functions has unique characteristics, making them suitable for different tasks and architectures. To put it simply, these functions are popular choices because they effectively handle complex data in neural networks. I'll be creating a future video to dive deeper into each of these common activation functions, exploring their characteristics and applications. Keep an eye out for this video if this sounds interesting to you. So in summary, why are nonlinear activation functions crucial? Well, they're crucial because they enable neural networks to learn complex nonlinear relationships in data. Okay, so let me know what you think of nonlinear neural network activation functions. Feel free to share your thoughts in the comments below. I want to hear what you think about this topic. Okay, thanks for watching.